Okay, everybody, welcome back. We're looking at lecture 15 today, which is going over thermodynamics and biochemical energetics. Um, your exam, if I'm not mistaken, is next week on Wednesday. I guess today is Sunday, so yeah, I guess it would be next week. Not this coming Wednesday, but the week after, if I'm not mistaken. Or Friday. I can't remember off the top of my head, but it is next week. So yeah, if you are watching this in fall 2025, there you go. And yeah. So, this one might be a little bit longer than usual, but hopefully I can kind of go through what's important and what's not important, but we'll see. So, um yeah, so they're going to cover, I mean they covered delta G, they cover standard free energy, delta G naught, relationship between the two, delta G and Q, coupling, ATP. Hopefully ATP is relatively familiar to people right now. And then auto oxidation reduction, which are two interesting concepts. So for what do we mean by thermo? So thermodynamics is referring to um, a measure of the ability of the system to do work. So if I have a negative value, it means that this reaction is doing work on the system. It is releasing energy. And work is a process of energy transfer between systems and its surrounding. So yeah, work is just some form of energy, right? We just assign energy from work. And so if a reaction is spontaneous and it's negative delta G, it is releasing energy and it is therefore doing work on the system and the surroundings. Hopefully you remember this from like physics or chemistry or something, right? So what is delta G for a reaction? A plus this reaction here, A plus B goes to C plus D. Basically, the difference in chemical free energy between the initial state and the final state. So if I have my reaction coordinate diagram, right, the initial state here versus the final state here, right, is what I'm looking for, right? What is the difference between this and this in terms of energy? And this difference here, right, is how much energy is released and how much work is done on the system. If instead my reaction coordinate diagram looks like this instead, right, that means that instead of this doing work on the system, that means that the system has to do work on this, right? Because the difference between these two is from here to here, right? So it's not a negative value, it's a positive value, right? So basically, this is a driving force for reaction. So how is the reaction going to happen? Is it not, right? Um, it basically measures how far away from equilibrium we are, and we'll cover that later. Basically, a negative means spontaneous, right? So exergonic. So exer, release, external, gonic, energy related, right? And then positive is ender, so within, and then gonic, which is energy. So basically, external energy, so release of energy versus internal energy of like absorbing energy, right? So it tells us whether it occurs in the forward direction, like this reaction here, or if it occurs in the reverse direction, like this reaction here. It does not tell us anything about the rate. The rate is that K, if you remember from a couple lectures back, right? The rate is the K value, and the K value is actually is determined or affected by the delta G double dagger, which we remember from here, right? Can't remember how to draw a G, guys. That's not how I draw G's. Oh, there we go. Okay, double dagger, right? So this is what that's affected by, right? There's a term in there for the rate. The rate is different from equilibrium. They're not the same thing, right? So what is delta G? So delta G, right, is looking at the initial concentrations versus the final concentrations at equilibrium, right? So for the derivation that we're going to go through, we're going to set these as the initials, and these are the at equilibriums, right, for A, B, C, and D. And this is our reaction formula here, right? And we're going to use that to figure out delta G. So basically what we're doing is we're comparing a reaction in the state it's in versus its equilibrium state. So any reaction wants to achieve and reach equilibrium, right? But in the body, we don't allow things to reach equilibrium, because if we allowed things to reach equilibrium, we would die, right? The whole point of our body is that nothing is in equilibrium, and because nothing is in equilibrium, we can constantly create and destroy things and make new things and keep ourselves alive, basically, right? So basically what we're doing here, right, if you remember from Gen Chem, right, you're basically taking the delta G, right? So the overall delta G is going to be equal to the energy in the initial state, right, minus the energy in the equilibrium state. So delta G naught prime, I think, if I'm not mistaken, and then delta G naught. I can't remember the exact notation, but or sorry, delta. This is actually technically Q. I guess it is delta G naught, or but it is basically Q, right? So for this section right here at this is going to be KQ. Rephrase this, yeah. This is going to be KQ and this is going to be Q, right? The reaction quotient versus the equilibrium constant, right? So basically we're saying, okay, given the position that we're at now, how far away are we from equilibrium? That's what we're taking the difference, right? That's what this minus sign, the minus sign is a difference, right? As opposed to addition, that's the sum, right? This is the difference, right? So we're taking the difference between the state we're currently at versus the state at which we're at equilibrium, right? Which is what is shown down here. Right, and here's some definitions for you if you need those. And of course, remember, when you're doing these, they will ask you to do calculations on these. I'll go over those a little bit later, but if you don't have to use this because it'll simplify it for you, but remember that the temperature is always in Kelvin when you're doing these kinds of equations. Generally speaking, you don't have to do this conversion in your head, because as I'll show you down below, they actually give you the numbers, but that's generally speaking how you do it. So delta G naught, right, is the difference in chemical free energy in the standard condition. So what is the standard condition? The standard condition is everything is 1 molar. Everything is 1 molar. The temperature is, I believe, 298 Kelvin or something like that, and the amount of water is 55 molar and pH 7. And it actually should show you. There should be a slide that shows you somewhere. But right, basically the whole point is that you're trying to figure out the basically trying to figure out the what's the equilibrium of this equation of this system without external forces acting on it or any other system pulling products away or putting reactants in or something like that, right? So why do we set it to 0 to these to 1? Well, because this equation here with the reaction quotient is Q, right? If we set everything here to 1, right, the natural log of 1 is 0, and so this whole term basically cancels out, and what you're left with is just this negative RT ln KEQ, right, which just gives you delta G naught, right? And so, based off of that, right, we have this. And if you convert this into log form, you can use this, but from now on, you guys can just use 5 log AQ. A space here. You can just use this. Right? Basically, all of this stuff here cancels out to 5, around 5 kilojoules per mole. Make sure it's in kilojoules, right? Kilojoules is very important, right? Kilojoules. Right? Not anything else. Kilojoules. Right? And then here are the standard conditions that we use this under. So pH 7, 55 molar, and then KEQ makes the exact same assumptions. Right? Do you have to understand how this works, like, vaguely? Sure. I don't think you have to understand the depths of it, right? But you should be able to use it to do some math. That's basically the gist of what you need to know. You don't need to know the complete underlying interconnecting network of how things work and why this equation is the way it is, but generally speaking, hopefully what you're learning here from what I'm telling you is enough to get you through the course. If it was enough to get me through the course, and you shouldn't need to do more than this. So here we're going to take the difference, like I said, the difference, right? So what is the difference between these two states, right? How far away are we from equilibrium compared to our initial state? Is our initial state very far from equilibrium? Is it close to equilibrium? What is it, right? So basically, right, we're going to take this RT ln KEQ as our delta G naught, right? This is where we want to be. This is where our equilibrium is. And this RT ln Q is where we're at right now, right? So we're taking the difference between where we want to be and where we're at, right? I know it says plus here, but that's just a rearrangement of this equation, right? This is just being pulled out in front of that, right? And this negative sign goes with it, right? So this goes all the way up in front of this, right? So this technically here, this delta G naught here has a negative inside of it. It may not be canceled out depending on what the KEQ is, right? But just remember that this negative sign is there. So if we simplify this, right, go through all of this, right, you get this equation, right? Basically, right, we're taking what our delta G is at equilibrium, and we're comparing it to our initial state, right? See these numbers again. So KEQ and Q, right? The difference between equilibrium and the initial state, right? And notice here that the -5 is here, and this is a +5, right? It doesn't matter if you put this big term here out in front of this term, right? As long as you're consistent with your math, right? So delta G naught and KEQ, they're intrinsic properties of a substrate and product, right? Remember, this whole scheme, right, is not dependent on it's just dependent on the stability of the substrate and the stability of the product. It's not dependent on anything else, right? It's not dependent on how much there is, right? It's just dependent on the product and the reactant, right? I guess it is technically dependent on how much there is, right? But it's just a measure of stability, right? Which one is more stable, right? When we do all of this delta G, like this Q, all this stuff, right? We're taking into account how far we are away from equilibrium, right? Because we want to reach that equilibrium state. So while delta G naught is constant, right? It's just the difference between these two, right? Q is very much variable, right? Q changes depending on the situation. And it changes and influences the magnitude of this delta G, right? So it changes the driving force towards equilibrium, right? If we're farther away from equilibrium, right, the driving force towards equilibrium will be much larger. If the driving force between delta G naught prime and delta G naught is smaller, then there's going to be less of a driving force towards equilibrium, right? So if we look here, right, so yeah, so this right here, so remember, this delta G naught prime is, here, let me move these. Actually, yeah, you know what, let's go ahead and screenshot this and pull it down. Let's go ahead and take this, and we'll copy this, and we'll move it down here so I can kind of show you guys what I'm thinking. I guess it is down here, but, oh shoot, here, okay, cool. So, right, if I look at this, right, delta G naught prime is right here, and delta G prime is here. So let's use the blue for this one, right? Kind of a pretty bad circle, but you get the idea, right? What I'm trying to showcase here, right, is the difference. So this blue, right, is this guy right here, right? And the red is this guy right here. So, right, in glycolysis reaction, right, in the heart, right, we're looking at the heart specifically, right, not the liver in this case because it's grayed out, right? The delta G prime, if you did the math, right, you did the negative RT ln KEQ, right, would be negative 17 kilojoules per mole. So this value here is negative 17 kilojoules per mole, right? But the delta G prime in the heart is negative 24. So we're -7 off, -7 kilojoules off here, right? Which means that we are not close to equilibrium, right? So there's a lot to be done, right? So we still have to go towards equilibrium, right? Because we want this value here to be 0, close to 0, right? If we're at equilibrium, we don't want it to be close to 0 because we'd be dying. But if we want this, as this number gets closer to 0, right, that means we are at equilibrium, right, or closer to equilibrium, right? So the idea here is that this -7 right here, right, pushes us further and further away from equilibrium, right? Hopefully that kind of makes sense, right? Because when these two are equal and opposite, right, that means that this would be 0, right? And that would mean the reaction is no longer basically not working anymore, right? So if we look at this, right, -17, -24, right, it's clearly more spontaneous and more likely to occur with the concentrations given, right? So it's probably what's happening, right, is that we're providing a lot more reactants for this reaction, right? And then because we're giving so much reactants, right, this reaction is being forced to go even more, right? Same thing with this reaction here, right? -17, -26, right? The only weird one here is the cleavage of this. The cleavage of fructose 1,6-bisphosphate, right, is going from +23 to -6. So we're actually gaining like +17 here, right? So this is like +17, right? So that means that we're actually getting relatively close to equilibrium, right? Which means that we probably have a lot more products here than reactants, right? So the equilibrium is pushing in one direction, right? And then in this case here, we have a +17 here. We're probably getting closer to the reactants here, right? The idea here is that this is this kind of delta G, this Q term is basically modulating how far we are from equilibrium, right? Closer to 0, equilibrium, closer to equilibrium, farther from 0, farther from equilibrium, right? And pretty sure that's all I really want to talk about for yeah. Hopefully that makes sense, right? The idea is that the main point of this is that this delta G prime term, right, is dependent on delta G prime naught, right? And also the Q value, right? And so if we're farther away from equilibrium, that means that the external conditions of the environment are actually promoting that. They're promoting this larger delta G value. Right? And if we're closer to 0, that means that the environment is actually favoring going towards 0. The coupling biochemical reactions, basically what this means is that if you're given a reaction, right, in this case A to B, B to C, these are basically additive. And they're additive because the product of one reactant goes in as a reactant for another. So basically you can cancel these out. You can add them together. So A goes to C, and then these just add together, G1 and G2. Example of this is coupling through the TCA cycle. So citrate to isocitrate is endergonic, right? Not favorable, right? However, if we couple it to oxidation of isocitrate and to alpha ketoglutarate and the rest of this stuff, right, we can add these together, right? So +5 minus 21. And notice, right, the product of one reactant, the product of one goes in as the reactant for the other. And these cancel. This and this cancel out, right? And so you're left with, just do they show the full reaction? Yeah, left with this, right? Notice how in this reaction scheme here, right, all that's happened is that the isocitrate has disappeared, right? Everything else is the same. And they've added these numbers together. So plus 5, minus 21, minus 16, overall endergonic, even though the first reaction is not spontaneous, right? And I actually did have something like this show up on my exam. So you should be able to do this very quickly, right? So, here we have this, right? You should be able to pick out which ones cancel. So if I look at this, right, ATP plus water makes PI-ADP, right? So I can see that in this case, the PI and the PI would cancel, right? Which tells me that, oh, and also the water cancels, right? So the water will also cancel. So basically, glucose ADP will be on one side, glucose and ATP, sorry, glucose 6-phosphate ADP, and glucose and ATP will be on the other. So ATP glucose, glucose 6-phosphate ADP, right? So those are all there. Now, if you look at these delta Gs, I know that they're additive, right? So if we look at this, negative 30.5 kilojoules per mole, and then 13.8, add these together, and I get 16.7, right? The Qs also add together, but what you should know is that basically it's the difference between them. Oh gosh. Right. So if we look at this, the Q for this is 10 to the 6, right? So very spontaneous. The Q for this is 10 to the negative third, right? And so the Q for this would be 10 to the negative third, right? And that's just if you basically take these, right, and add these up, they would cancel. These two would cancel with this, right? That's one way of looking at it. I personally didn't really have to do any kind of math involving the Q's. They usually mostly ask you about the delta G, not primes. Yeah, so here's an example, right? So direct coupling, yeah. So the first step of glycolysis actually uses this technique here. Yeah, and hopefully you guys know how ATP works at this point. We got adenosine triphosphate, diphosphate, monophosphate. Tri, di, mono. Adenosine is just a nucleotide, right? You'll have to memorize these in 441, but we're not in 441 right now. So, yeah. This is a number to actually, I would say, memorize it. Just keep in mind that this is what the ATP hydrolysis has for its delta G value. Like around negative 31 kilojoules, negative 30 kilojoules per mole. So why is this hydrolysis very favorable? It's because breaking apart this bond, right, releases charge repulsion. So like all these negative phosphates, right, because they like don't want to be bonded together like that, right? If you break it apart, that negative charge repulsion stops, right? The other thing is that the resonance stabilization of the product, right? So the ADP that you form, is basically a little bit more stable than than ATP because there's one less phosphate group and more resonance, right? So it's kinetically stable, right? That means it has a higher active energy. It has a very high activation energy for hydrolysis, but once it gets to that top, the drop is really large, is the point. So with the hydrolysis, right, you see all these negative charges are interacting, right? If you hydrolyze it, these two charges separate, right? And so now this product, right, is very resonance stabilized, right? Once it's been deprotonated, right? There's like 4 different resonance forms for this guy, right? And this guy is just off on his own, right? He has less charge repulsion. This other product is very stable because of resonance, right? All that jazz. There are other molecules that have higher transfer potentials than ATP, like creatine, phosphatidylpyruvate, but we end up using ATP. So, right, so transfer of phosphate from ATP can provide energy to drive reactions. So, an example of this is glutamine synthetase, which you will learn about in 441, which is an enzyme that takes glutamate and turns it into glutamine. And you'll actually eventually learn that glutamate can be made from the citric acid cycle through, I believe it's alpha ketoglutarate, if I'm not mistaken, right? So basically what we're doing, right, is we're using ammonia, right, from the urea cycle or something, right, and we're combining it with ATP, right, in this intermediate step, right, to make this unstable intermediate, right, and then using this ammonia as a nucleophile to make glutamine, right? So basically, this reaction is so spontaneous that this reaction is now possible, even if this reaction is not as, like, basically, you're making this a good leaving group, right? So by adding this here, you're making this a good leaving group and you're coupling it, right? So normally just adding a phosphate onto here is probably not favorable, right? But because ATP being hydrolyzed is so favorable, right, it's okay to add this onto this, onto the glutamate molecule. And enzymes that usually use up ATP are called synthetase, but there is a weird case in the citric acid cycle, called succinyl-CoA synthetase, if I'm not mistaken. That is a bit weird because they actually discovered the enzyme in the reverse direction. So we'll cover that when we do citric acid cycle, but just be aware that there's a weird convention with this. So if we look at oxidation reduction, right, this one should be hopefully relatively simple, right? So the simple way of talking about this, right, is that the more carbon-oxygen bonds there are, right, the more oxidized it is. And the more carbon-hydrogen bonds there are, or just bonds to hydrogen there are in general, that's reduction, right? So if we look at this, right, this carbon, right, so these carbons here have lost all their hydrogens, right? So there's no so these carbon hydrogen bonds are reducing, right? But if you look here, it's only carbon oxygen bonds. So this has been oxidized. If you look here, oxygen goes from only bonding to itself, very very oxidized, being bonded to two hydrogens, right? So it's going to be reduced. The other way you can do this is just by using your Gen Chem knowledge, right? So let's think about it. So hydrogen has a charge of +1 each, and then oxygens are -2 each, generally speaking, right? So you go +12 right here. You go, and you'd go -12, right? And so that would mean that carbon would probably have to be something like 0, right? If you look at this, right, any gas is just 0, right? And then if we look at CO2 here, both oxygens have a -2 charge, so a total of -4, which means that carbon has to have a +4 charge. And oxygen is -2 here, and these two H's are +2 total combined. So you can tell, right? So oxygen goes from 0 to -2, so it is reduced, right? It's gaining electrons, right? Oil rig, you can think about it, right? Oxidation is losing electrons and reduction is gaining electrons, so we're going from a more positive number to a more negative number. And then we're going from a, for the carbon here, we're going from a neutral, neutral just 0, right, to a +4 value, so it's being oxidized, right? And notice how negative this is, right? So yeah, this idea that respiration, right, is just basically we're taking glucose and we're going beep 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 beep, and eventually, right, we drop down to this, right? Now you might be wondering, why can't we just go from here straight to here? Well, systems are really bad at actually storing energy, so if we do it in small chunks, it's actually a lot better because it's a little bit more efficient. But basically, if you try and drop from here to here, right, all of that energy is released as heat and you'll basically start a fire, right? So that's not what you want to do, right? You want to harness that energy. You don't want to waste it, right? And so if we just did this massive drop, we just waste all of our energy, which is not what we want. Yeah, and this is the other way you can do it. This is very similar to how I do it, right? But this is basically looking at it bond by bond. So you should be able to do this, right? You should be able to look at look at this carbon and say, what's the oxidation of this carbon, right? So if there's a CH bond, right, -1. If there's a CC bond, 0. And there's a +1 bond, a +1 for every O, N, and S, right? So basically what's happening, right, is because these oxygens are more electronegative than carbon, they're pulling electron density away. So it gives this carbon a partial positive. But these hydrogens are like a little bit less electronegative, so they actually give their electrons to carbon a little bit more, right? So basically if you add these together, -1, -2, +1, that's -1. So this carbon would have a -1 oxidation number case. And the other way you can do this is using my method here, which is just C2 well, I'm forgetting to do this now. C2H6 O, right? I think I did this right. 1 2 3 4 5 6 1 2, yeah. So if we do this, right, these hydrogens are +1 each, plus 6. The O is -2, and so each carbon would have to be +2 in this case. Oh, sorry, -2. Is right? Yeah, yeah. So each carbon has to be -2 in this case. But yeah, that is that's the main gist of how this works, right? This is better. This version here is better if you're looking at the individual charges, right? And I think it's totally fine to do this method if you're just looking at the overall structure. If they're asking for specific atom charges, do this method. Right? This is just a bit more accurate. Yeah. And actually, just to preface this, actually, so this is the average, right? If you were to look at this carbon right here separately, there would be 3 -1 charges, right? Coming from these hydrogens. So there's one hydrogen with a -1, another one with a -1, and another one with a -1. So that this is -3 and this is -1. So notice how the total adds up to -4, right? But this isn't super accurate here because what this is doing is giving you the average, right? Which isn't actually what's happening here. That's why I said that this is better if you're looking at individual atoms, right? So all of these added together is -4, but this carbon here has a much lower oxidation number, or more negative oxidation number compared to this carbon here. And so click on the carbon with the, yeah, so basically, right, you should be able to tell me based off of these, what's the oxidation of these. So, right, carbon hydrogen bonds, there's 4 of them, so -4, right? If you look at this, right, -1, -2, -3, +1, so -2, right? -1, -2, right? 2 bonds to oxygen, right? So +2 on this carbon here, so this would be 0. And then if we look at this, +1, +2, +3, and then a -1 here, so +2. And then +1, +2, +3, +4. This is going to be an oxidation of +4, right? And of course, you should be able to do the same method as before. So if you do CH4, the formula here, each hydrogen is +1, so +4 here. The carbon is +4, right? That checks out. This formula here would be CH3OH, right? This is +3 for each one for these hydrogens, right? +1 for this hydrogen. This would be -2, right? So +3 plus +4 there, right? -2, right? This is going to be right now. Wait a minute. This is Yeah, actually, ignore this. This is... I have to go through this a little bit more, because that one... I think I'm messing up my own method here. Definitely works here. Yeah, I feel like I'm messing it up, but... Can you tell I'm just winging it a little bit? But yeah, basically, you got to make sure that you're doing this the correct way here. Otherwise, it'll get a bit messy. But generally speaking, they'll only ask you to do these kinds of calculations, so I would just stick to what they're doing here. There is a way to do this, I just can't remember how this works for these guys specifically, because it's a little bit different. Because, of course, it has to be. And then we move on to these. So yeah, this is just a nice slide about NAD being an electron carrier, right? So you probably covered this a little bit in OChem, maybe, but like basically what's happening here is this hydrogen is being added, right? And this is the reduced form, right? Because we're adding a carbon-hydrogen bond, and this is the oxidized form, right? So we have one less carbon-hydrogen bond. And then here we again have the reduced versus oxidized form, right? So we're adding a hydrogen right here, right? And then removing a hydrogen there. I don't think the rest of this is that important. I think what you should keep in mind is here. So like, yeah, FAD example is another electron carrier, right? And basically you get another reduction reaction, right? So here's an addition here and one addition here. This is a radical mechanism, it seems like, so I would be a little bit hesitant to about this one. This is a bit of a weirder one, but same principle, right? It's being reduced, you're adding two hydrogens. And vitamin B2 and B3. So riboflavin, FAD, niacin, NAD, right? And these are important in these oxidation reduction reactions, which we use in our cells. Other than that, though, that should be it for this lecture. I do want to apologize about this. I would just say for these questions, just use their method, because it seems like they, for some reason I life of me cannot remember how this works with these, but like for this, right, it does work up here. It's just that for these, it's the average, and it's obviously not the case that each carbon is -2 in this situation, right? It's the average is -2 per, right? But if you look at the individual atoms, it's -1 for one and -3 for the other, right? And so actually wait, did I just mess up the? Oh yeah, hold on a minute. I'm just being a clown. Wait. Yeah, hold on. This is yeah. Sorry, why did I mess that up? Sorry, yeah. So H, right? These are +1. These are +1 each, so +4. This carbon will be -4. Yeah. I don't know. I don't know how I messed that up. But yeah. This, right, is going to be CH3OH. Each one of these is going to be +3, +1, the +4 there, -2 here. This is going to be -2 as a result of that, right? Yeah. I think I just messed up my math when I was doing it a little bit earlier. I was doing this the other day and it actually worked out, right? But same thing here, right? This is going to be H2O +2 here, -2 here. This is going to be 0. For this one, COOH, right? -2 for each one of these, so -4 total, +1. This is going to be, oh, sorry, there's actually 2 H's. So CHO2. -4 here, +2 here, +2 on this carbon. And this is just CO2, which is -4 total and +4 total. So hopefully that makes sense. Apologies for messing that up, but as you can tell, I am tired. Um. Anyways, that's all there is to this lecture. Hopefully it was helpful. Again, apologies for the confusion with those oxidation reduction states. But just keep in mind that if they're asking for like specific atoms within a molecule, you should probably do this method here, where you're counting the carbon hydrogen, carbon oxygen bonds or whatever, right? And if they're asking for just the overall average oxidation number for an element, you can just do this method here, right? But it depends on what the question is asking. Normally, they're just going to ask you to do this, right? On the exam, they'll genuinely just ask you to give the oxidation number for a specific carbon, right? And yeah, so just for reference, right? The reason that for this, like for down here, these guys, right? Like I could just do this method and get the same answer as they have here is because these only have one carbon in them each, right? This has two carbons, right? So it gets a little bit more messy, right? Because you have to take the oxidation of this and this, but because these only have one carbon each, right? You don't have to do any of that, right? Yeah. Other than that, hopefully this was helpful. And yeah, have a good one, guys.